All right, hello class. Welcome back. It is you guys took the AP exam on Monday, and I gave you a couple days off, so you're back. Um, while you were gone, I tried foraging for the first time. It was pretty exciting. So I'm not done with my first piece yet, but this is my knife that's coming along. So as you can see, it's almost exactly the length of a piece of paper. So it's about 11 inches long. It was a railroad spike. So the original railroad spike was maybe this long. So it's basically doubled in length just by, you hammer it and it extends. This was the sort of the head of the spike. So it's still probably going to get a little bit longer as well because if you look at the thickness, it's pretty thick. So I would say it's about twice the length of, or twice the thickness of a regular knife. So it'll need to get thinned out a little bit. It's quite heavy. It's about, I don't know how heavy it is, but it's pretty heavy. It's also not flat. So anyways, what I'm going to do is I'm going to thin it out, and then I'm going to drill holes. I have a drill press, and I'll drill holes here, and then I'll heat treat it. So I'll get it super hot, and then cool it off in oil. And when you heat treat it, it makes it. That's what hardens the blade. And then after that, it's just I've got some wood for a handle. So I'll put the handle in, and I have pins that will go into the holes, and then it's just sharpening and polishing. So yeah, I'm pretty happy about it. I like the this is called a drop tip. So it doesn't, if you think about a chef's knife, it normally just kind of curves up and then the top of the knife is flat. But this has the drop tip, so it's very stabby. All right. So hello everyone. Let's see who's here. Hey Fu, hey Rowan, hey Zach, hey Alex, hey Alex. Hey Luigi, hey Nick, hey Justin, and hey Mo. All right. So you guys chose to study special relativity. And before I gave you guys the choice, I had planned to teach you guys about complex numbers because complex numbers are used extensively in advanced circuits and in quantum mechanics. But then you guys chose special relativity, but I had already made my lesson plan. So I'm just going to spend 2 days and teach you about complex numbers, okay? And then we'll do special relativity. Once we're done with special relativity, we will probably have time to do a little bit of quantum mechanics. And at that time, I will bring back this complex number stuff because complex numbers are used all the time in advanced mathematics and physics. Okay. So hopefully you can learn a little bit about maybe that you didn't know before. So today is going to be probably truly review, and then tomorrow we'll learn about Euler's theorem and some of the more advanced stuff with complex numbers. Okay. So first of all, we can talk about the imaginary number. Okay. And the imaginary number is I. But yeah, when I first went to college, I planned on majoring in electrical engineering, and electrical engineers actually use J for the imaginary number, and the reason is that I is used for electric current, so they just have a different variable. So, when I'm reading a textbook, I automatically will read both of these as the imaginary number. So you should too. Okay. Some textbooks use I, some textbooks use J. So it has the property that I squared is -1. Okay. A complex number is a number. So the typical variables for complex numbers are z, w, u, and v. Those are the most common, variables that are representing complex numbers. So a complex number can be written as z equals x plus I, y, where x and y are real numbers. So these are both real numbers. So I'll say they are part of the set of real numbers. Okay, so there are a couple of fundamental operations for complex numbers. One of the fundamental operations is called conjugation. And for complex conjugation, you basically replace I with negative I. Okay? So the symbol for conjugation, there's two commonly used symbols. One is to put a bar over the variable, and the other one is to put a star next to it. So I'll use both of them interchangeably. Okay, so and it would be equal to x minus iy. All right. So one of the things that is useful is to I'm going to talk about two other operations. There's another operation called the real part. So the real part is denoted by RE, kind of like a curly RE of Z. And the real part of Z is just the part that's not multiplied by I. So the real part of Z is X. Okay. Then there is the imaginary part, which is denoted by a curly IM, like that. Imaginary part of Z is the number that multiplies I, so that would be equal to Y. Too bright. Hang on a second. All right. So then there's this thing that's called the complex plane. And so what you do is you can actually graph a complex number. And so the what is the y-axis is the imaginary part of Z. And then The horizontal axis is the real part of z. Okay? So let's suppose I had the complex number z equals 2 plus I. All right? So what that means is you should go over 2 and up 1. And so this is the complex number z. All right? Now, all right? Now, if I wanted to do the complex conjugate, it would be 2 minus I. So you can see that we would go over 2 and then down. That's what complex conjugation does. Okay? So there's another interesting thing we can define, which is called the modulus of a complex number. And the modulus of a complex number is defined as absolute value of z, and it's equal to the square root of z times its complex conjugate. Okay? So what do we do when we multiply complex numbers? We just use FOIL, and then we collect like terms. Okay, it's really easy to multiply complex numbers. So for example, z times z bar, or z star, would be x plus iy times x minus iy. All right? So what if I FOIL that out? I get first times first is x squared. Outside would be x times minus iy, so minus ixy. And then you have inside, which is iy times x, so plus ixy. And then the last term is going to be iy times minus iy, which would be negative I squared y squared, which is... So anyways, what you can see is that the ixy and the negative ixy cancel out. We have negative times I squared, so that's negative times negative is positive, and we get x squared plus y squared. So the modulus is square root of x squared plus y squared. All right? So what does that mean in terms of geometry? Well, it actually means the modulus is the distance of the complex number from the origin. Okay? So that's the modulus. The modulus is the distance of the complex number from the origin. Okay? So what we can go ahead and do, now we can use the modulus to define the inverse of a complex number. So what does it mean to have like 1 over w, for example? Well, what you do is you take 1 over w and you multiply it by 1. Because you multiply anything by 1, it's just itself. Okay. So what if I have... so I'm going to write 1 in the form of w bar over w bar. Okay. Now you can see on the denominator I have w times w bar, so that's just the modulus squared. Okay. So this is w bar over modulus squared. All right. So that's how you do 1 over a complex number. So let's just do some examples, okay? Let's say that u equals 5 minus 3i, and v equals 2 plus I. All right. So what if I wanted to do u plus v, and what if I wanted to know the modulus of u plus v, for example? Well, if I do u plus v, it's going to be the modulus of 5 minus 3i plus 2 plus I. So if I collect like terms, I have 5 plus 2 is 7. And negative 3i plus I is negative 2i. So now I need the modulus of that, which basically means do the Pythagorean theorem. Well, square root of 49 plus 4 is 53. So that's the modulus. Okay. Let's do another example. What if I wanted to know u squared over v? All right. So I'm going to think of u squared as u times u. All right. And then 1 over v, I'm going to think of as v bar over modulus of v squared. All right. So what's the modulus of v squared? It's going to be x squared plus y squared. So it's going to be square root of 2 squared plus 1 squared, root 5. Oops. So the modulus of v is root 5. That means that modulus squared is 5. Okay. So I have 1/5. And then I have u times u, which is 5 minus 3i times 5 minus 3i times 2 minus I. That's v bar. Okay. So now I got to do FOIL twice. Okay, so let me do FOIL twice. This one's going to be 25 minus 15i minus 15i minus 9. So it looks like this is 16 minus 30i. I think I did that right. So now we have 16 minus 30i times 2 minus I over 5. And so I'm foiling that. First is going to be 16 times 2, which is 32. Outside is going to be minus 16i. Inside is going to be minus 60i. Last is going to be negative I times negative I, which is negative 1 times 30. So negative 30. And all this is over 5. So now collecting like terms. We've got 2 minus 76i over 5, which is going to be 0.4 minus 15.2i. Woo! So that's how you do it. Okay. I want to go back to the complex plane. Okay. What if I have my complex plane? all right? And if I do u plus w, so let's say I have u, which is 5 minus 3i. So here's u, and v is 2 plus I, all right? Now if I do u plus v we said was 7 minus 2i. So this is u plus v. So actually, it turns out that if you add two complex numbers, okay, if you add two complex numbers, it's just the same way as adding vectors, okay, the parallelogram rule. That's kind of cool. So that's how you add complex numbers graphically. We're going to talk tomorrow about how to multiply and divide complex numbers graphically, but we need another theorem to do that. So this form of a complex number in the form x plus iy, this is called the rectangular form of a complex number, okay? And there's another form, it's called the polar form of a complex number, all right? And the polar form is when you write the complex number as r times cosine of theta plus I sine of theta, okay? Where, so let's take our original comp. You can see that 2 has got to equal r cosine of theta. And then we have 1 is r sine of theta. Okay? So to get something in polar form, what we notice is that basically r is the modulus, x squared, square root of x squared plus y squared. And the angle is the inverse tangent of y over x. Okay? So for our example complex number of 2 plus I, our modulus is square root of 2 squared plus 1 squared. So that's square root of 5. And then our angle is inverse tangent of 1/2. Which is about 27 degrees. Okay? So I could write 2 plus I could write it as square root of 5 times cosine of 27 degrees plus I times 27, I sine of 27 degrees. Like that. All right, so what is the sort of geometrical meaning of the polar form? Basically, it's a complex number that makes an angle of 27 degrees with the real axis and has a distance from the origin of square root of 5. So it's a way of thinking about complex numbers in terms of angle and distance from the origin. Tomorrow, we'll be talking about a third form of writing complex numbers, which is called the exponential form. And the exponential form makes it really easy to multiply and divide complex numbers. Okay. So that's my lesson for today. I hope you enjoyed it. I think today was probably mostly review for most of you, and then tomorrow will be mostly new stuff for most of you. Okay? So have a nice afternoon, and I hope to show you a big update on my knife